Hello, my name is Bhan Prakash and I'm studying EC department, and I'm today talking about the topic matrix representation of non-homogeneous systems, and from ECA. Matrix representation of non-homogeneous systems, a formal approach. Matrix representation of non-homogeneous systems, a formal approach. This presentation will provide formal approach to understanding the matrix representations. This presentation will provide a formal approach to understanding the matrix. Presentation forward formal approach. Formal approach, good approach, maybe. I don't know what approach formal. I think it is respective approach to understanding the matrix representation of non-homogeneous systems. We will explore the mathematical foundations and practical applications of this concept. Mathematical foundations means it's how it is developed and how it is done. Concept started. Understanding non-homogeneous systems. Non-homogeneous systems are mathematical models that include both homogeneous and non-homogeneous components. Homogeneous means same type of components. I think non-homogeneous, not the same components. These systems are often used to describe real-world phenomena. Means real-world phenomena like linear equations alone represent a non-homogeneous system with matrices. Means non-common systems with matrices. Just like a graph, I think matrices are often used to describe equation for ax plus ba plus c. I think linear equations alone. Linear equations can also be yx is equals to my plus c, m something like that, x is equals to my plus c. M is the slope of the line. It helps in the how slope is to the graph. Just like this, homogeneous and non-homogeneous components also can be represented in a graph. If there are different ways solving homogeneous equations, matrix equations. To solve the non-homogeneous matrix equation, matrix representation of non-homogeneous systems has numerous practical applications including fields such as engineering, economics, physics, and computation and space questions. These applications highlight the versatility and importance of this formal approach. Analyzing the stability of non-homogeneous systems. Stability of a non-homogeneous system is a crucial consideration as it determines the long-term behavior of the system. The matrix represented can be used to assess the stability of this system using techniques such as eigenvalues analysis. Eigenvalues with the help of an eigenvalue analysis, we can assess the stability of a matrix, stability of a non-homogeneous systems. Numerical techniques for non-homogeneous matrix equations. For non-homogeneous matrix equations, in many real-world applications, analytical solutions to non-homogeneous matrix equations may not be feasible. In such cases, numerical techniques such as iterative methods, approximation algorithms can be employed to obtain approximate solution, analytical solutions to non-homogeneous matrix, not common matrix. Analytical solutions may not be feasible. In such cases, numerical techniques such as iterative methods. Iterative methods can be used in real life, just like maps. Graphs it can be used in plotting the color of a different points of a graph. I think it can be used. This non-homogeneous matrix can be used in that. Iterative methods or approximation algorithms can be employed to approximate solutions. It can be used in graphs to find approximate solutions of a matrix equations. Matrix representation of non-homogeneous systems can be indicated with optimization techniques to solve complex problems involving constraints objectives. This approach can be particularly useful in decision making and resource allocation. Just like this graph, this matrix can be used in different salesman problem. Another subject, salesman problem is a way which is used with the iteration method. Iteration method can be used in a salesman method, in that it is a very useful way to spending money and going to different places instead of going a long and very much pricely and costly way of traveling and long distances without much of a difference. We can use these iterative methods, which is made with the help of non-homogeneous equations. Iterative methods and approximation algorithms can be employed to obtain approximate solutions for a way to move from one place to another and make the journey very easier by passing through every point. Matrix representation of non-homogeneous systems can be integrated with optimizing techniques to solve complex problems involving constraints and objectives. This approach can be particularly useful in decision making, just like the salesman problem. The non-homogeneous or homogeneous equations can be used in in trying to solve those equations, probably with the help of programs, with the help of mathematics. Non-homogeneous matrix iterative method can be used. Resource allocation means important, less important, not much important. Like those information can be stored in different ways, just like that resource allocation scenarios. And next is modeling non-homogeneous equations with differential equation. In some cases, non-homogeneous system can be represented as a differential equation. The matrix representation can be combined with techniques from differential equation theory to analyze and solve these more complex non-homogeneous models. From a differential equation theory to analyze and solve these more complex non-homogeneous solutions. In some cases, non-homogeneous equations can be represented using differential equations. Differential equations are dx it can be used in differential represented it can be represented through differential equations. Non-homogeneous systems with differential equations can be represented through differential equations. Not that non-homogeneous systems can be represented using differential equations. The matrix representation can be combined with techniques from differential equation theory to analyze and solve these more complex non-homogeneous models. Just like this homogeneous differential equations and non-homogeneous differential equations, it can be used independent variable and having a function of independent variable instead of 0 on the other side of the equation, and functions of independent variables on the other side means that having a function of independent variables instead of a 0. Independent variables, having independent variables on the left hand side and functions of dependent variables on the right hand side. Just like this. This y1 plus ay is equals to fx. Left hand side is a independent variable. Fx is a function of dependent variable which is dependent on y1 plus ay. Having a function of independent variable instead of 0 on the other side of the equation means function of independent variable means fx has an independent variable instead of a 0 in the place of x, and a function of the independent variable on the side. Functions of dependent means the left side hand side y1 plus ay is dependent on the f of x and value the of x. X value is a independent variable which is used in different fields. Fx is a function in a big method. And interdisciplinary perspective on non-homogeneous equation. The study of non-homogeneous systems has implications and applications across various disciplines including mathematics, physics, engineering, and computer science. Collaboration and cross-pollination of ideas can be led to innovative solutions. Limitations and future directions in non-homogeneous research systems. While the matrix representation of non-homogeneous systems is a powerful, versatile approach, there are still limitations and open questions that require further research and exploration. Identifying these areas can guide future development in these fields. Industrial approach. Industrial approach. There are still limitations and open questions that require further research and exploration. Identifying these areas guide future development in this. Conclusion. Importance of matrix representation in non-homogeneous equation. In conclusion, matrix representation of a non-homogeneous systems provide a formal, rigorous approach to understanding and solving these complex mathematical models and applications and implications of this concept span numerous disciplines, highlighting its significance in scientific academic community. In conclusion, non-homogeneous system provides a formal and rigorous approach to understanding and solving these complex mathematical models. The applications and implications of this concept span numerous disciplines like programming, material science, energy, and various biochemistry, and also various applications. It is used in various applications like sound recording and research and academic community. Thank you for giving me opportunity for talking.